Hi and welcome to another Dech Academy video. Here I have question 19 of the June 2013 Maths Waec exam. And the question says, well, even before I started the question, I think it's important to review the concept of the alternate segment theorem, which I know a lot of people find confusing. So if you have a configuration as follows, where you have a circle with an inscribed triangle and a tangent, such that the tangent, as you can see, like the tangent obviously meets the circle at one point. So, and that's this point. If that point is such that it coincides with the vertex of the inscribed triangle, I'm going to take a few seconds to digest that. Basically, if you have this configuration, this point here where this vertex and this tangent meet is an important point, right? Let's call that point, well, let's just be aware of that point. Now, let's consider this line, which is a chord to the circle. It makes an angle with a tangent here, and I'm calling this angle x. Alternate segment theorem says that this angle is equal to this angle. It also says that the angle this blue chord here makes with the tangent here is equal to that angle. And that's it. That's pretty much it. And if you recall from the name of the theorem, it's called alternate segment. And a circle can be divided into two parts, into two segments, for instance, by a chord. So if I just draw a chord here, I have this as a segment, this is another segment. It is pretty much the same thing we have here. If I consider this as a chord, this blue line here, I'll be interested with the two chords with two lines that touch a tangent. So I'm looking at this one first. If I look at this line first, I can think of the circle as having been divided into two segments. So this one as one segment, and this whole big area as another segment. So please keep that in mind. Keep that in mind. Now, this line and the tangent have this angle. And this angle, as you can see, is in this segment, right? You agree that this angle is in this segment, or it's basically crosses this segment, if you see what I mean. Now, what alternate segment theorem tells you is that this angle is equal to this angle here in the alternate segment. If you remember, this is one segment, while this area is another segment. This angle is not equal to this angle. This angle is close to the segment. It's not equal to this angle here, which is close to the segment as well. It's equal to the one that's far away in the alternate segment. That's one way to remember it. Okay? Similarly, if you consider the other chord which touches the tangent, this blue one here, it makes an angle with the tangent here, y. So I'm always looking at the angle where I'm always looking at the angle. The angle that I draw such that I can just draw it smoothly without any interruptions with the other line. So, I'm looking at this chord and I'm not looking at this angle because I crossed the other line. Even when I looked at this chord, I didn't look at this angle with the tangent because it crosses this line. I looked at this angle with the tangent. And that's the same thing I'm doing here. I'm picking this chord and considering this angle with the tangent, this angle y. What alternate segment theorem tells you is that this angle y is equal to this angle in the alternate segment, not this. Okay, so let's pause. If this line is the chord we're considering, that means this is a segment and this whole area is another segment, right? Okay, now this angle is essentially in this segment, and this angle is equal to an angle in the alternate segment, in the other segment. So the angle in this segment, this angle y, not this angle here, because this angle, I don't want to say because, but not this angle here. And the way to remember is that this angle is so close to this segment, and not this angle here. And the way to remember this is this angle is also close to this segment. As you can see, y is considered to be in this segment, and this angle here and this angle here are essentially right next to, the boundary of this segment. So you don't consider them. It's the one that's far away within the triangle. So in other words, you need to remember that. I'll use another color. you have an inscribed triangle in a circle, you have a tangent, and the tangent coincides with the points that the tangent touches the circle coincides with the vertex of the inscribed triangle. As far as here, I mean, this is a vertex, this is the tangent, and this is where they meet. You pick the two chords from the inscribed triangle, so this one and this one, that touch the tangent, and you consider the angle each chord makes with the tangent. In this case, we consider this angle, which is here, and according to alternate segment theorem, and you can consider that angle to be in this tangent. According to alternate segment theorem, this angle is equal to this angle in the other segment, not this one and this one, which are very close to this segment, but the one that's so far away. Similarly, for y, the same applies. You pick this chord, the other chord that touches the tangent, you look at the angle it makes with the tangent, you know, the angle you can draw without having to cross the other tangent. So I'm not looking at that one, but I'm looking at this angle. And according to alternate segment theorem, this angle here is equal to this angle here in the alternate segment. Remember, we're considering this chord, which divides the circle into this segment and that segment. And this angle here is considered to be in this segment. This angle here and this angle here within the triangle are very close to this segment, but those are not the ones we're considering. It's this one that's far away in the other segment. This angle y is equal to that. So let me just, another way to draw this will be to, I'm going to apply this theory, but let me just lay it out clearly so you can see. I have a circle. Well, that's supposed to be a circle. I have a circle. I have a sort of triangle inscribed in the circle. And I have a tangent. And you can see that this triangle has a vertex here. I mean, it's better if I use a different color. This triangle, wow, has a vertex here. And the tangent, I could use a blue line for that, is as follows. As you can see, the vertex and the points at which the tangent meets the circle coincide there. And what we're trying to say is that this angle here, so you've considered the two chords, this one and this one, the ones that actually touch the tangent. And you say, well, the angle this chord makes with the tangent, this one here, this angle here, is equal to this angle in the other segment. So this is one segment, and this is another segment. I mean, this can be very confusing, but I hope you're getting the point. And then you consider the other chord that touches the tangent, and you say, well, this chord here makes this angle with tangent, which is equal to this angle in the other tangent, in the other segment. As you can see, this line divides the circle into this segment and that segment. And this angle here is considered to be in this segment. This angle here and here are very close to this segment. You don't want them, you want this one. So this is equal to this. That's kind of a crude way of explaining this. Another way would just be to memorize, the image of the circle. But I hope it makes sense. Now I'm going to apply it, so hopefully it makes sense when I do. So if I read the question, it says in the diagram is a tangent to the circle UYW at W. As you can see, the tangent at W, just over here. This is the tangent at W. This is W here. And the question goes on to say that if WY is parallel to UV, and it's telling you that this line UV is parallel to WY. It also tells you that angle UYW is 95 degrees, and also tells you that angle UWY is 46 degrees. And it asks you to find what angle UVW is. So this is actually V. So there's kind of a mistake in it, Doran. So angle UVW. I'm going to call that alpha, just for the sake of simplicity. Now, I just spoke about alternate segment theorem. Now, let's look at the two chords that touch the tangent. As you can see, we have the circle, we have the configuration for the application of this law. We have the circle, we have the tangent to the circle, and we have the inscribed triangle UWY, so which has the vertex here that coincides with the point where the tangent touches the circle. So we have the configuration in disguise. It's not obvious, but you can see it's here now. And we look at the two chords. So this one, WY, and UW, the ones that touch the tangent, and we consider them separately. Let's look at YW. YW divides the circle into two regions, two segments. This segment and this segment. Now, the angle YW makes with the tangent is this angle. I'm not considering this one because I crossed the other chord. I consider the angle I can draw without crossing the chord. That's a way to remember it. So this angle here is equal to this angle here. So I'm going to call this angle X. Oh, also notice that because YW and VU are parallel, this angle here must correspond with angle alpha. So basically, this is alpha and this X is alpha. So, I mean, you might as well say this is alpha and this is X. So, for those of you that don't recall corresponding angles, think of it this way. I have two parallel lines, and I have this horizontal line here joining them. This angle is equal to this angle because they correspond. They correspond in the sense that this is a line and this is the angle it makes with this horizontal line. This is another line which is parallel to this line, and it makes this angle with the same horizontal line. Therefore, according to the corresponding angle rule, these two shaded angles are equal. And that's what I've done here. This angle, this line is, wow, it's so hard to draw straight lines. This line, WY, has been given to be parallel to VU. VU. And they both, I mean, this horizontal line touches both of them. Just in the same manner here. And according to corresponding angle, the rule of corresponding angles, this angle here, the WY makes with the tangent, if you want to call it the tangent, or the horizontal line, must be equal to this angle here. I mean, look at this, what I just showed you here, and what I just did here. You'll agree. So, basically, we know that this angle here is equal to this angle, which is also equal to this angle alpha we're looking for. So if you consider triangle UWY, we know two of the angles, but we don't know what X is. If we find X, we know alpha because alpha is equal to X, as we deduced. So I'll just make this bigger. This triangle I should make this triangle neater. UYW. So we know this angle is 46 degrees. We know this angle is 95 degrees. And we know, we've called this angle X. Now, if you remember from your maths lessons, the sum of angles in a triangle is 180 degrees. In any triangle, the sum of all angles is 180 degrees. So using that rule here, it means that in this triangle here, X plus 95 plus 46 must be equal to 180 degrees. That means X plus 141. is equal to 180 degrees. So 95 plus 46 is 141. Therefore, making x subject formula, I'm subtracting 141 from both sides. X is equal to, well, let me do it this way. Let me step by step. I'm subtracting 141 from both sides, because I do the same thing to the left hand side as I do to the right hand side when I'm dealing with equations. Simplifying this gives that x, 141 minus 141 is 0, so that goes away. So I have x plus 0 equals, because 141 minus 141 is 0, is equals to 180 minus 141, which is 39. So x plus 0 is x, is equals to 39 degrees. And as I've shown you previously, alpha is x. We deduced that using the corresponding angles rule. Alpha is that, which is equal to x. Alpha is equal to x, therefore alpha is 39 degrees. So I'll just go back to the diagram and say what I said. Say what I just did. From the alternate segment theorem, this angle here is equal to this angle here. From corresponding angles, this angle here is equal to this angle here. This angle UVW that we were interested in. And that is all. Thank you.